When the current is flowing in this direction, that is from left hand side towards right hand side, the magnetic needle tend to move at this position, that is the rotation it takes towards the left. What is force? Force is a certain energy. Okay, so the energy required in order to move any of the particles is said to be a force. If suppose you take a current carrying conductor, a conductor which carries a current. So if there is a current, movement of charges gives you a magnetic force. So consider a conductor. Hello everyone, I am Brinda, Faculty of Physics from Vidhyaashram Pre-University College, Mysuru, welcoming you all to Chapter 4, Moving Charges and Magnetism, Session 1. So from this chapter, it is the first session what I am dealing with. So what is meant by a magnetic field will be the concept under this chapter. Okay, so it is like you're going to check out how is the existence of magnetic field occurred. Okay, and what made the existence of the magnetic field, and that is all about the electric field. Okay, so having the base foundation of the electric field and electric charges and electricity, you just introduce a magnetic field. Okay, so you have studied about the unification. Unification means the existence of electric field, introduced a new concept called as magnetic field, and finally it's like interrelated. The moving charges produces magnetic field, and the magnetic field in return it produces the electric field. That is called as unifying in electromagnetism concept. Both are unique, both are one. Electromagnetic effect. Okay. So now this concept was introduced by Hans Christian Oersted. So he gave an experiment wherein he conducted an experiment which shows the presence of the magnetic field. So Ampere, he supported this concept by saying that moving charges, the charges, Q charges, the charges which moves produces the magnetic field. Wherein it was taken by Michael Faraday, and he told that the magnetic effect, in return it produces electricity. Okay, vice versa concept was taken by Ampere as well as Michael Faraday. Finally, it came into the hands of Maxwell, and he introduced the concept of unification, that is electromagnetic effect. Okay, so having all this, the Christian Oersted, he gave an experiment, and experiment was conducted as there was a needle which was placed and a current was allowed to flow through a conductor. By that, they introduced a concept called as magnetic field. So magnet is kept at the bottom, the current carrying conductor is kept at the top. So it is all about the unification what we are studying. So unification means the electric field and magnetic field together, it is called as unification concept. You have studied this in your first PU, very first chapter, that is physical world. Studies something about unification as well as something about reduction. So this is all about unification what we are studying, and reducing means splitting up like fission, fusion and all those stuff. This term is said to be unified term, wherein you are fusing electric field and magnetic field all together within a same event. Okay, so now Christian Oersted, Hans Christian Oersted, what did he do? He conducted an experiment. And how did it look like? So there was a needle over here, compass needle, which was placed like this, and the needle was, if suppose this is a pointer and this is these two sides are the pointers, and this is a needle what is kept. So here there was a flow of current through one conductor, and the flow of current is said to be current I. When the current is flowing in this direction, that is from left hand side towards right hand side, the magnetic needle tend to move at this position, that is the rotation it takes towards the left. You will understand which is left and which is right when I do the swimming rule, Ampere's swimming rule. Clear with that? So the deflection was towards the other side, then the other side of the needle, the deflection is towards the right side. This was the case. Now suppose if the current was changing its direction. So the direction of the current is shifted now. So this will be the direction of the current from right to left. So what happens to the needle which is present? So suppose if this is the needle, the standard position of the needle which is given over here, then the needle is said to deflect upside. This is towards up, this is towards down. So it is vice versa. This moves in anti-clockwise direction and this is in clockwise direction. So I hope you got to know what exactly the results of Christian Oersted experiment which he conducted. Okay. So next we are coming on to Ampere's swimming rule. You have seen the previous one. You have your needle which is deflected towards left side. Why do I call it as left side and right side? Instead I can call it as up and down. That is according to your swimming rule. Swimming rule in the sense, suppose if this is a conductor, and current is flowing in this direction, that is left to right. Left hand side towards right hand side. And suppose a man is swimming over here. If suppose this is his hands and his legs, he is swimming. This is a swimming pool wherein a current, the conductor is placed in this manner and current is said to move from his feet to head. The flow of current is from feet towards head. It is entering the feet and leaving at the head. That is the direction of the current I. Okay, so this direction shows the current I. Okay, and now you can see a man is swimming and his face is towards the conductor. This is his face towards the conductor. So now what happens to the needle? The needle starts deflecting towards his left hand side. So when you just, if this is a conductor, when you just fall onto the conductor facing the floor or facing the ground, what happens? Your right hand, this is your left hand. So your magnetic needle fluctuates, that is needle turn, anti-clockwise direction, turn towards the left hand side. Got it? Similar way, you have got a wire and now suppose the current is flowing in this manner opposite to the direction. What happens now? It turns towards the left. Clear with that? So if suppose a man's body is facing down over like this and he is swimming the other way, what happens? The direction of the needle moves from, suppose you turn the other way and the direction is this way now. So you fall over here. So you're facing the floor. Now the current deflects towards right hand side. That is towards your right hand side, which is called as clockwise direction. So I hope you got to know what is actually Ampere's swimming rule. How he related the swimming into the Ampere's rule on the basis of electric field as well as the magnetic field's coexistence. Now next we have magnetic force on a moving charge. What is force? Force is a certain energy. Okay, so the energy required in order to move any of the particles is said to be a force. So here we are checking out magnetic force on a moving charge. A charge is said to be moving. When a charge is moving, you can see that there is an effect of magnetic field. Okay, so now here what is that you're checking? Magnetic force on a moving charge. You can't represent it as a static charge. It has to be a moving charge. So what is a force now? Force means a certain energy required for a charge to move. As a result, you will get another force and that force is nothing but your magnetic force. So now you know that the static charges, we were studying about the static charge. The static charge existed in your first chapter, call it as electrostatic potential and capacity. This is the second chapter. Your first chapter was electric charges and fields. So you studied all those concepts were under the static charges. So static charge means a stability, that is the charges which are in rest. Okay, static, stationary charges we are talking about. When we had studied the static charges, there was a presence of electric field. And electric field is given as force per unit charge. So you can just relate this as F is equal to E into Q. Okay, electric field into the charge. Now, we are studying about moving charge. Moving charge means there is a presence of electric field as well as magnetic field. Both the fields are present over here right now. So, the magnetic field representation, electric field, if you write this as E, your magnetic field can be represented by a symbol B. Okay, it is not M for magnetic field, it is B for magnetic field. And magnetic field has a property same as that of electric field, but the path is said to be a closed path. It doesn't have its start or ending point. Okay, the paths which are obtained is said to be closed path. Now, E and B, that is electric field and magnetic field, if this is a vector quantity, since its properties are same, even we get the directions for the magnetic field. So, this is also a vector quantity. So, what is meant by a vector quantity? Define vector quantity is the one which has scale, which has direction as well as magnitude. Direction through which, that is towards which direction the magnetic field is flowing, that is the direction. Magnitude means it is a value whichever you get. So, magnitude with direction together it gives you the vector quantity, and this magnetic field B is a vector quantity. So, now anything, if suppose this is a plane, so the magnetic field entering a plane gives you a cross product, leaving that plane gives you a dot product. Okay, so the cross product and dot product things you have studied in your PUC. That is the first PU concepts these dot product and cross products are. Okay, so now any magnetic field getting into the plane will be cross product. It determines the cross product, and leaving the plane determines the dot product. So that is all about your magnetic force. So now, if we consider a plane, so here we consider this is a plane, okay? And now we consider a charge over here at this point, and the charge has got mass m and it is moving with certain velocity which is perpendicular to the magnetic field. And if suppose this is a magnetic field, according to the right hand rule, remember right hand rule, if suppose this is a right hand now, right hand rule means you have to give a thumbs up, okay? So if it is a thumbs up, you can see your finger, that is a thumb finger which shows the direction of the current, and your curled finger, the completely curled finger shows the direction of the magnetic field. If your thumb shows the direction of current, your curled fingers shows the direction of the magnetic field. That is what it is. So this is a curled fingers showing the direction of magnetic field, which makes an angle theta with respect to the velocity of the charge q. And suppose if this is a charge q, the force is said to be moved upwards. So this is a F vector, call it as a force. So how do you give a force now? So force can be given as F is equal to, you just give charge q into the field. The field is what existed, that is vector v, velocity, cross product and vector B. You have force is equal to Q into the field, that is electric field. It comes under your static charges. In case of your magnetic effect over here, that is magnetic field, force is in terms, it is given as Q into vector V into vector B. And now it can be called as, it is cross product. It means to say that the force is represented in cross product. It means the force is perpendicular to the velocity as well as to the magnetic field. So what is the relation of this force with respect to velocity and magnetic field? It is perpendicular to each other. That is why we have mentioned over cross over here. So this is a vector quantity. If suppose we need a magnitude of this equation, you can rewrite this as F. Without a vector, we are writing only the magnitude of this Q we be associated with the trigonometric function, call it as sine theta. So it is QVB sine theta, whose formula is very important. That is force due to the magnetic field is said to be QVB sine theta. Theta is the angle made over here with respect to the angles it has occupied, force, magnetic field and velocities. Okay, so when can you say your F is said to be maximum and F is said to be 0? F is maximum when your theta is 90 degree. That means when theta is perpendicular, you have got your maximum force. Maximum force. That is when theta is 90 degree, what is your sine theta? Sine theta turns out to be 1. So you have got F is equal to QVB. And when it is 0, when theta is 180 or 0 degree, so you have sine theta is equal to 0, sine 0 is 0, so the complete thing goes out to be 0. That is how you calculate. So I hope you got to know why it is a cross product, because of its perpendicular thing, and then what is the magnitude. It is written as QVB sine theta, and how is that cases, two cases, F is equal to maximum and F is equal to 0. How is that? You have got when angle is 90 degree and when angle is 1. That is all about your magnetic force on the moving charges, what you have studied. So now, having this concept, when can you say that F is equal to B? When do you get this condition? This condition is got when Q is 1, V value also should be 1 meter per second, Q value should be 1 ampere and theta value should be 90 degree, so that sine theta gives you 1. Okay, so these are the condition. When you have a unit charge which is moving with unit velocity and it makes an angle unit angle, then you will have force is equal to the field, that is the magnetic field. Having this concept, I will have to introduce 1 Tesla. So what is meant by 1 Tesla? Remember students, the magnetic field's SI unit is said to be, SI unit is what? It is Tesla, and 1 Tesla is equal to 10 raised to minus 4, it is Gauss. Okay, so this is the relation. You can even write it as Gauss, but 1 Tesla will be equal to 10 to the power of minus 4 Gauss. So that is all about your unit. So you have to define Tesla now. Okay, in order to define Tesla, you have to have a condition. When can you say that B is equal to 1 Tesla? You have F is equal to QVB sine theta. So B is equal to F divided by QV sine theta. So you have to get completely as 1. So when can you say this is 1? When you have a unit force, unit charge, unit velocity and theta is 90 degree. The force is perpendicular to it. So theta should be 90 degrees. So magnetic field at a point is 1 Tesla. Suppose you had considered a plane and a force over here, magnetic field, velocity, theta, all are perpendicular to each other. So when that is the case, if this is a force, this is a magnetic field, this is a velocity. A magnetic field at a point, if suppose at this point, the magnetic field at a point is said to be 1 Tesla. If here it should be 1 Tesla, if a positive charges of 1 coulomb is moving in right angles to magnetic field, okay, that means the motion of 1 coulomb of charge should move with the right angles to the magnetic field with the velocity of 1 meter per second. It should experience a force of 1 Newton when it moves, when that is 1 coulomb of charge moves with the velocity of 1 meter per second. So you have got your Q is said to be 1 coulomb of charge and you have velocity as 1 meter per second square and you have your force obtained as 1 Newton. So force is over, charge is over, velocity over and it should be perpendicular to it. Then you can say B, that is the magnetic field, experiences 1 Tesla. So 1 Tesla definition is with respect to these concepts, whatever you take. Magnetic field at a point is said to be 1 Tesla if a positive 1 coulomb of charge moving at theta is at right angles to the magnetic field. You have to see magnetic field So with the velocity of 1 meter per second, so second square comes out for the acceleration, this is velocity, so 1 meter per second, F is equal to 1 Newton, it experiences a force of 1 Newton. So that is all about your 1 Tesla, and now we are getting on to Lorentz force. So what is Lorentz force? Lorentz force is nothing but the same, that the force which is given as for electric field, the force is Q into E. Okay, and for magnetic field the force is said to be Q into V vector into B vector. This is the vector form of the force due to electric field and the force due to magnetic field. Together you merge it and give the Lorentz force, and that is Lorentz for the total force is equal to, you have merged both also, so it is Q into E plus Q into V cross product of vector B. So it is merging electric force due to electric field and force due to magnetic field. So which is the common terms? Q common terms. So Q I'll take it out and I have vector E into V into cross product of vector V. So this is all about your force. This force is called as a Lorentz force. Lorentz force only due to electric field will be this, and this is due to electric field. Only due to magnetic field will be this one. Due to electric and magnetic field will be the last equation. So Lorentz force is the one which I have written over here. Got it? So I want all of you to mark this as important. This is an important concept of this chapter. So now we are checking on to the magnetic force on a current carrying conductor. If suppose you take a current carrying conductor, a conductor which carries a current. So if there is a current, movement of charges gives you a magnetic force. So consider a conductor. So here you write, consider a conductor of charge, certain charge, okay, Q, which has a length L. So you have charge Q, length L, and area of cross section to be A, and charge density is said to be N. Okay, that means there is a conductor whose length is L and it carries a current I in it, and there is number of charges in it, and the density of charge is said to be N, and within that certain area, and this area is called as A. Okay, if suppose you take a small area, it has got the charges Q whose density is called as N, and it is within the conductor of length L, and the current is flowing through it. So you have N into A into L. Okay, so the number of charges will be Q number of charges, and number of density is Q charges who is in N density in an area A within the certain length of the conductor. So having this, so this will be one set of equation. Now, if a current is flowing through, current I is flowing through a conductor, flowing through conductor. If a current I is flowing through a conductor, then we have certain drift velocity for the charges. The electrons are getting drifted. That produces the current over here. So now I is equal to NEAVD. This equation we have studied in the chapter 3, current electricity. Got it? Relation between the current and drift velocity is this term, and this I had told you it is an important derivation as well as the equation. Okay, so you have I is equal to NEA and VD. Okay, we know that E electron is nothing but your charge, so I can write NQA into VD, and I know I divided by A is equal to N into Q into VD. So what is I by A? It is current density as per your current electricity chapter. So N into Q into VD. That is why I told current and electricity chapter is the master chapter wherein you'll have to study. That is a scoring chapter. Clear? After which you can study the rest of the things. So now J is equal to NQVD. And we know that we have F is equal to the charge concept. This is the charge concept. N, A, L, Q into the force will be always perpendicular to velocity and the magnetic field. So consider this velocity as a drift velocity because we are considering a drift velocity here. Okay. So it's a family of velocity. Drift velocity is a family of velocity. So family lies with the family itself, lies in the place of that family itself. Okay. So now you have NQVD. So N, your Q and VD. It can be written as vector J. So I'll retain my AL here and take, since it is a vector quantity, I'll take the density here into vector B. So now we know that J is equal to, we have studied J is equal to I by A. That means I is equal to J into A. So J into A is here. So I can retain this as F is equal to current into vector L into vector B. Now the length is calculated in the direction of the field. The length is calculated in the direction of the field. So length also has got direction. So it is a vector quantity. So F is equal to I into L vector into B vector. So now because of this is a vector quantity which is converted into the magnitude as F is equal to ILB sine theta. Got it? This is how we calculate the magnetic force on a current carrying conductor. Okay, magnetic force on a current carrying conductor. Their existence, conductor means there exists a current, length, its field and theta. So it is IBL or ILB sine theta. So these two are the important concept for you to understand the magnetic force on a current carrying conductor. So in today's class, we have studied introductory part of the chapter 4, that is moving charges and magnetism, about unification, Hans Christian Oersted experiment, what did the experiment tell, swimming rule, that is Ampere swimming rule, and the magnetic force on a current carrying conductor as well as magnetic force on a charge which is moving. So on a charge you got QEB sine theta which relates the Lorentz force, and then you got magnetic force on a current carrying conductor of certain length L, that was given by ILB sine theta. In next class, let us study much more about the same chapter in the session 2, something about the velocity selectors and all, and until then have a good day. Thank you.